Hello, chemistry students. This is Miss Hallowell. I hope you're all doing well. At this point, we are at the point in our unit where we have learned about endo and exothermic reactions. We have learned about phase changes and how to identify based on a graph what endo and exothermic reactions look like. And so now we're going to use that knowledge to break bonds in a reaction and form bonds in order to identify whether reactions are endothermic or exothermic using their change in energy. Okay, so what you should have in front of you is something to write with so that you can follow along in these notes. You should also have the PowerPoint that I posted on Google Classroom. It's got information in there about energy and specifically bond energy and how you break and form bonds in a reaction. So what we're going to do is we're going to start out with a practice calculation. Your homework is going to be towards the end of this, where I'm going to draw out some calculations for you to solve on your own. So we're going to start with a familiar calculation, or a familiar reaction rather, which is the formation of water. So if we are forming water, we know that we have to add hydrogens and oxygens in order to form water. Notice that I added the balancing in here for you. You should be able to do that on your own. However, I figured at this point we should be able to identify that these coefficients are for our balanced equation. So what we're going to do is I'm going to give you what the structure of each of these molecules looks like, and then we'll dive in using the PowerPoint that you should have up from Google Classroom. So the first thing I'm going to do is I'm going to draw out what H2 looks like. So H2 looks like this. We've got two hydrogens with a single bond between them. We're going to identify that bonds are a single line. It represents 2 electrons. Now, according to the balanced equation, I have 2 of these. So I'm going to go ahead and draw 2 of them. We also have to add some oxygen in there. And so oxygen, when it forms a bond, is actually going to form a double bond with itself. So oxygen has a double bond with itself. So every time that you're going to be breaking a bond, it's either going to be a single bond, a double bond, or a triple bond, you have to break those electrons apart. So notice a single bond, we just have 2 electrons. A double bond is going to be 4 electrons. So any double bond is going to be a little harder to break than a single bond. And same with triple bond, that's going to be even harder. Got to break those attractions apart even more. And then we're going to notice we just have 1 because we have an invisible 1 coefficient in front of that oxygen. Now we're going to go ahead and form water. So in this reaction, we are breaking all of these bonds, and then we're going to be forming bonds to form water. And we have 2 waters. So as a reminder, this is what our water molecule looks like. There we are. So we've got 1 water molecule, 2 water molecules. So now we are representing here the structural formulas for each of these molecules in the reaction. Now we're going to go ahead and use our new bond energy knowledge. So remember that you should have that PowerPoint in front of you, and I would like you to turn to the PowerPoint slide that says average bond energies, and there's a big chart on the page, a big chart that says average bond energies and then gives you units in parentheses. So whenever we're reacting anything together, we're breaking the bonds of the original molecules in order to form bonds for the final molecule. So on our left side, in our reactants, we are representing bonds broken. So we need to break these bonds. And then in our product side, we're going to represent bonds formed. And if you notice earlier in the PowerPoint, it talks about how in order to break bonds, the system requires an energy input. And then in order to form bonds, it's going to release energy. The reaction is going to release energy. Okay, so let's take a look up here. We've got 1, 2 of these HH bonds. So we need to break 2 HH bonds Notice that I'm leaving space here. Make sure you're leaving space on this side so that we can show some calculations here. And we only have one oxygen-oxygen double bond, like this. So at this point, this is all we're representing. We're breaking 1, 2, 3 bonds here. You have to break all of the bonds in our reactants. So let's look at the chart that is on the average bond energies slide in our PowerPoint. If you look at that chart, we're gonna have 2 times the bond energy for an HH single bond. So it's actually the first bond on the top left-hand corner of that chart. It says HH, and then it says 436 kilojoules per mole. We'll get to those units at the end. Now we've got one oxygen-oxygen double bond. So now it gets a little trickier because you have to look in the chart for not the oxygen-oxygen single bond, the double bond. So when you look at that chart, all the way to the right-hand side, the fourth down from on the right-hand side, you have an oxygen-oxygen double bond, and it says 495. All right. So now that we've got this information, we know that 1 times 495 is just 495. Okay, I'm going to put a line here to separate us from broken, deformed. 2 times 436 is going to be 872. Let's go ahead and add those together because that's going to be the total energy for the bonds broken. So we've got 7, 6, 1367. All right, so our energy, we're going to represent it as energy of our reactants. That's what that little R stands for. Notice that it's a subscript. It's going to equal 1367, and our units are kilojoules per mole. Now we haven't seen those units before. Joules, remember, is energy. So we're representing energy of reactions. That's a throwback to physics. Energy of our reactants is in kilojoules. So kilojoules is just 1,000 times a joule. So a lot of energy. Okay. And then the per mole part is per mole of whatever substance we're using. So that's a throwback to our stoichiometry unit. Now we're going to go ahead and take a look at the bonds formed. So notice over here, we've got a lot of similar bonds formed. So if I look at this first water, we've got an HO bond. Well, that's the same idea as saying an OH bond, right? So HO or OH, it's the bond that's connecting an oxygen and a hydrogen, right? If I said 2 plus 3, that's the same thing as saying 3 plus 2. It's just backwards, but you're going to end up with the same result. So here I'm going to start with my oxygen. I'm going to go OH. Okay, there's one OH bond. We have another over here, that's 2. And then we have 3 OH, 4 OH. So we have 4 OH bonds to account for here. I could have said 4 HO bonds as well. It's the same thing. However, if you look at your bond energy chart, it actually just has OH. All right, so go ahead and find the OH bond energy on your chart. You should see that it's going to say 463 kilojoules per mole. All right, so go ahead and do that calculation. So if you do not have a calculator, you can go ahead and I'm going to pause for a sec to open my computer to do that calculation. Because that's hard to do in your head. And I got 1852. All right, notice that we don't have any other bonds. We just have 4 OH bonds. So we're actually all set on this side. We don't need to do any addition. So our energy of our products is 1852 kilojoules per mole. Okay, so if you have your slides open, you can go ahead and take a look at the next slide, which tells you about delta H, or the heat of reaction. Delta H is going to give you an equation. So you're going to do the energy of the reactants minus the energy of the products. Okay, the reason we're doing reactants minus products and not the reverse is that this is the energy that you're inputting to break the bonds, and this is the energy that you're releasing to form those bonds. So input minus release. So this equation is going to be helpful in determining the total bond energy of, or total energy of reaction of this reaction. So for our formation of water, we're going to have 1367 minus 1852. Those numbers I pulled from right here. When you do that subtraction, notice 13 is smaller than 18. You're actually going to end up with a negative number. So when you do the subtraction, you're going to get delta H is negative 485 kilojoules per mole. Go ahead and box that final answer. So if your change in heat is negative, that means the system, so this system is losing energy. So that means that energy is released from the system to the surroundings. If you think back to what we learned last week with endothermic and exothermic reactions, we can actually figure out whether or not this reaction is going to release energy or absorb energy overall. So, quick review: endothermic, exothermic. For an endothermic reaction, energy is absorbed. For an exothermic reaction, energy is released. And if we remember what those graphs look like, so here, if here's my coordinate plane, we've got energy absorbed, means we're inputting energy. So we're going to start here, we're going to end up here. So we're going to actually increase in our total energy, or our total heat in the reaction. Whereas for an exothermic reaction, we're going to start up, we're going to start with more energy, and we're going to lose energy overall. Okay, so take a look back here. If we have a negative delta H, so we have a negative heat of reaction, that means we lost energy in this reaction. That would mean that a negative delta H is an exothermic reaction. So go ahead and add that to your notes on exothermic reactions. That delta H is negative, that means it's exothermic. It's releasing energy from the system to the surroundings. So the surroundings are going to feel like that reaction is hot because the surroundings are getting energy from it. Whereas an endothermic reaction, you're going to have an overall input of energy into that reaction. So it'll feel a little bit cold to the surroundings because the surroundings are, or the system is taking energy from the surroundings. So this reaction, the formation of water, actually releases energy into the atmosphere, into the surroundings. All right, our last part. So now what I'm going to do is I'm going to give you 2 problems to practice on your own, and that's going to be your assignment. So your first reaction is going to look like this. So I'm going to run through the beginning part pretty quickly so that you're able to get started soon on these and use this video to help you. So we're going to have a reaction where we have 2 carbons plus 2 hydrogen molecules to form this giant molecule. Not giant, but bigger molecule. So what this is going to look like is the carbons are actually going to be separated from each other. They're not bonded to each other. So carbon's not bonded to anything, which means you don't actually have to break any bonds for carbon at the beginning. However, we are going to have two H2s, kind of like we had in our formation of water. So these are our reactants, and we're going to end up with this molecule that looks a little more complicated. All right, so this molecule right here actually is 1, 2, 3. This is a bond. It's a double bond, but it's still just one bond. 4, 5. 5 bonds. So you're going to go ahead and set up bonds broken. And bonds formed. All right. So for this reaction, I'm going to help you out real quick. Notice that we have no bonds for these carbons at the beginning, so you can actually ignore them when you're trying to figure out which bonds you're breaking in the beginning of the reaction. You just have 2 HH bonds to worry about. All right, I'm gonna let you finish those calculations there. Over here, I did say earlier that we needed to break 5 bonds. Okay, remember that this is just one bond, even though it's a double bond. So here we've got a CH bond, another CH bond. If we jump to the other side, we've got a third CH bond and a fourth CH bond. So we've got 4 CH bonds. Okay, one of the things I like to do to help me keep track of my bonds is anytime I've written them in this section down here, I've accounted for them, I'm going to go ahead and eliminate them on my structure with a different color marker or a different color pen. And so then they kind of look like X's when I've accounted for them. Okay, my last bond to account for is this middle bond. So I just have 1 CC double bond. Now, when you're looking at your bond energy chart, if you look, there's an energy for a CC single bond. That energy is 348. What you actually want is the energy for the CC double bond, which is 614. Okay, so make sure you're looking at the energies for each of the bonds and making sure that you're not using a single bond if you're actually looking for a double bond energy. All right, so you're going to go ahead and solve that the same way we solved during the practice. All right, and our second reaction, so reaction number 2, whoops. For reaction number 2, we are going to start with 2 bonds of nitrogen and oxygen to each other. And we're going to separate into, whoops. Give me 1 second. And 2 plus O2. There we go. All right, so what this looks like, sorry about this, there's no coefficient there. It's supposed to be an invisible 1. This bond here actually looks like an NO double bond. And when we look at our products, we know that the oxygen is usually a double bond to itself. And the nitrogen actually forms a triple bond, which is pretty exciting. We haven't seen a triple bond before. So let's make sure that when we're identifying our bonds bonds broken and bonds formed, we're using the amount of bonds that we see on the page. Okay, so we've got bonds broken. Bonds formed. All right, so I'm going to leave you to it. Go ahead and identify the bonds that you see here. Just to clarify, I only see 3 bonds here. And that means that, oh, no. Sorry, just double checking. I don't know if anyone else caught this error. Miss Hallowell made an error. Whoops. Okay, so now we've got 2 NO bonds. Now I'm clarifying we've got 2 NO bonds. Wow, I'm sorry about that. All right, it's a good thing we double check work here. So we've got actually 1, 2, 3, 4 total bonds that you're going to be breaking. So 2 in the reactants, 2 in the products. All right, I'm going to leave you to it. So to clarify, last bit of information, what you should be doing is number 1, solving for delta H in each reaction. And number 2, when you're done, upload a picture or pictures of your work to the Google Classroom assignment. Okay, so remember that you're uploading a picture of your work to Google Classroom. That's how I will be grading you this week. So the assignment is not a Google form, it's on Google Classroom. All right, I hope this helped, and as always, reach out if you have any questions.